9 physics topic and also a little bit of the year 10 topic. It is a transfer of energy from one point to another, okay? But the key thing is with waves is that there is no net transfer of matter. Energy is transferred, but matter is not. I throw a ball to you, that's a net transfer of matter. It is not a wave, okay? However, water, you make a disturbance in the pond, the water waves start rippling, and there's a little leaf a little distance away, and that little leaf suddenly starts going up and down with kinetic and potential energy, okay? The water there's been no net movement of water, but we've been able to transfer energy, okay? So just remember that, no net transfer of matter. There are two ways that waves can travel, but they share two common features. There has to be a disturbance, whether it's a mechanical wave or an electromagnetic wave. You need to have some sort of disturbance, and then there needs to be a medium, or field. We'll use the term field because we know light doesn't require a medium or matter. It can travel in a vacuum. So a disturbance or a medium or a field for the disturbance to travel through. This should be fairly revision to you. The two types that we can lump them into depends on the particle displacement, whether they are displaced in the direction of wave propagation or at right angles to it. Okay? So, can anyone recall back to year 9 physics of an example of a longitudinal wave where the particles are displaced in the same direction? Yes? Sound, absolutely. Sound is the go-to answer. Okay? There's also pressure waves, which is really a big, if you had an explosion, then you're going to get a massive pressure wave that travels out. It's pushing the particles away from the disturbance towards the person that's receiving it. One could argue dominoes. You set your dominoes up. And when they fall, they are falling in the direction of the wave propagation. But really, you can only do it once, and then you've got to reset them. Did anyone ever have a fortunate childhood where you had a set of dominoes that you could set up and make little domino tracks? Cool, me too. I had a couple of big boxes of the dominoes, and in them they had 500 dominoes, but then they had these sets of 20, and they were on this plastic bracket, and so all you had to do was just go like that, and they'd all line up, and then you carefully line it down. All right, and then that was 20, and you could set them up. There were some right angle turns as well, like some 90-degree curves, and you could go, and all of it, they'd all line up. You'd carefully place it down, and then they'd all fall over. One of the boxes, I used to get the catalogues from the toy stores, and one of the domino catalogues had this special domino placer that you stack all your dominoes in, and you, like a little car, you literally roll it along, and it would lay out the dominoes at the perfect spacing. All right, obviously it has to be a flat surface or else they'd fall over. Man, I wish I got that, but never did. It was on my Christmas wish list, but, it wasn't. Hey? A slinky can demonstrate I need a volunteer on this side, someone who's well behaved. Aiden, come on. Come on, so too. All right. Grab the slinky. Now, in the middle of the table, please. Now, gents, I'm going to do all the hard work here because Aiden can't be trusted, but please just direct your attention. What we have here is each ring sort of represents the particles in the medium. Okay? It could be air, and so it just represents a particle at that point. I've saved a bit of energy here. I'm going to send out a pulse. I want you to watch the pulse. Ready? Here we go. There it goes. There it comes back. Oh, we did 2.5. I'll do that again. Ready? Cool. 1, 2, 3. Cool. You can see the pulse travel. Although there's no net movement of Slinky. The Slinky is still where it is. We didn't see the Slinky suddenly shift towards Aiden. The next thing I'd like you to look at, if you can, just focus on one ring, and as the pulse travels through it, you would see that the particle simply travels forwards and backwards and then back to its equilibrium point. Ready? Pick one ring and watch it. Okay, you should have seen hopefully it went towards and then away and then back to its equilibrium point. Okay? So, that is an example of a slinky. For those of you that weren't able to see that, I've placed on the OneNote a couple of videos. I know, have you already watched them? Oh, it's exciting. There's a few demos here, and I've loaded them up. All right. Am I wearing the same shirt? Oh, jeez. I've got like 30 shirts, so that's actually quite improbable. Here we go. Slow motion. Can't really see anything. This is boring. Oh, hang on. Am I wearing the same tie? No. Here we go. Maybe. Send the pulse away. It is. Oh, come on. This is boring now. I'm going to unlike it. Just wait. That was transverse. There. Okay. There. You can see. Okay. Yeah. This is a horrible video. What a waste of time. All right. Unlike transverse is where they are displaced at right angles. So, yes, thank you. Mexican wave. Can anyone think of any others? There are many.
Light.
Good. Light and electromagnetic radiation. All parts. Go. Yes. Surface water. Someone wrote slinky again. So yeah, our slinky can demonstrate both, if you can recall back. Some kid said last year shaking a towel, and I was like, yeah, okay. You could get a rope or a garden hose and give it a flick. So if you sent a pulse down the rope, as the pulse travels down the rope is moving up and down as the pulse travels left to right. So that is a transverse wave as well. I'm just going to quickly color code them. If you have a highlighter, do the same. So longitudinal, displaced in the same direction. Transverse, displaced at right angles. Okay. While you're highlighting that, I'm very quickly going to find, hopefully I've got, oh dear, is it in year 9? Videos in year 9, videos. Here we go. Go laptop, go. All right, check out these bad boys. This is the year 10 cadets on a Friday. Okay. We're ready. Now, these are simple models. Okay, obviously, as you look into it, you're looking at atoms, and as they get closer together, they're going to exert a repulsive force, and as they impart their kinetic energy or transfer their kinetic energy through their movement. The next thing is, when they move apart, there's now an area where they're too far apart and it might pull them back. So we will look more at areas of compression and rarefaction later. But check out these bad boys. Look at them go. Now they're working obviously in harmony here to produce these waves. But again, you simply watch... Oh, come on. You simply watch one of the blokes, he's just moving up and down. Meanwhile, we can kind of see the wave travelling transverse to the particle's movement. You can also pause it at some... You could do distance over time. You could have someone running alongside. You could measure the speed of the wave. You could find the wavelength, which is the point between successive peaks or troughs. You could calculate how far apart they are in numbers of soldiers. So they're demonstrating the wave quite well.
So if you die in the same spot you're born, what does that make your velocity?
Average or instantaneous?
Average.
Hey, get up here. Now, It's this demo, this model is far too important, so Aiden's not going to do much. Here we go. There's the pulse. You send it down, and it reflects back. Later on in the course, we're going to look at the nature of the pulse. You might notice that it goes out that way and then returns back to the other side. It actually gets flipped over. We'll look at that in more detail. But again, I've got to displace it a fair amount, and friction kind of sort of locks the slinky in. But if you just watch one little link, it's moving now left and right, or away from you towards you, as the wave propagates towards Aiden and away from Aiden. So if you just watch one slinky, it should really only be travelling left and right. Thank you, Aiden. Let it go. There's the demo done.
That's another big spring you got there.
No. We're not going to look at that. I also loaded up this now. This has some interesting applets. Can we zoom out on this bad boy? Yes, we can. All right. So, gents, longitudinal. These are some good animated GIFs. Have a look at them, please. The link is on the OneNote if you just want to stare at it for a while. What we have here is a disturbance. So it's just a plain plain bar just moving backwards and forwards. And as it moves backwards and forwards, you can see it makes sort of a pressure wave. And you can see this pressure wave traveling along at a constant speed. All right? Even though the particles are involved in transferring that pressure wave, all the particles are doing, and this little red dot here is simply going backwards and forwards. Oh, pressure, low pressure, high pressure, low pressure, high pressure. When it's under an area, it's getting pushed from high pressure to low pressure. Think of balloon. The air gets pushed from high to low. So that particle is just trying to go from high pressure to low pressure. So when he's in an area of high pressure, he's trying to move into that area of rarefaction. But as he gets there, then the low pressure's behind him. So he's constantly getting pushed backwards and forwards. He hasn't got a chance to rest because this disturbance is making a nice periodic disturbance. It's just continually going backwards and forwards. Okay? So again, compression, rarefaction, compression, rarefaction. We will put some label diagrams to this. Earthquakes. Oh, here we go. Transverse waves. For some strange reason, they haven't animated this one. But again, this is now a transverse wave. Pick one dot, and it's just moving up and down as the wave. You can almost picture the wave traveling along at a constant speed. Now, we did say surface waves, but it gets a little bit tricky. Surface waves are not quite transverse, they're not quite longitudinal. This model kind of says that they are at the top, they're kind of a bit of both. They're moving in the direction as well as transverse, okay? And the further away from the surface you get, you're not going to see any surface waves. The closer you get to the surface, the greater the displacement of the particles. And then you've got some Rayleigh surface waves. This is what is seen in, I think, earthquakes, not P-type, but S-type pressure waves, S-waves in earthquakes. So we will have a talk about S-waves. See, the funny thing about earthquakes is, and actually I was listening to a podcast of Elon Musk. He's a bit of a weirdo, but he's currently building a Hyperloop, which is an underground tunnel from New York to the other side, San Francisco, and this tube, you suck all of the air out because you don't want air resistance, and then you travel along at 1,000 kilometers an hour, and you can get, quicker than an airplane, and then you get to the other side of America. And he was saying, earthquakes, the nature of the earthquake waves are only really damaging the surface. If you go down 30 feet or 30 meters or 60 or however deep you want to go, there's not much displacement deep down. So it's not like the earthquake is going to take your tube and suddenly crack it. It's only if it's on the surface, like roads and bridges, they're the ones that go kaput. But if you're 30 meters underground, your tunnel is going to be relatively undisturbed.
So with where he said she had high pride.
Yes, yes it was. Yes. All right, so, gents, we can lump these waves into two types, mechanical waves and EMR waves. Could you please quietly read those two while I bring up another animated GIF, please? Please, quietly. EMR. Quietly read those two, please. Here we go. Okay, and now quietly direct your eyes towards the board. This is a model of an electromagnetic wave. Now, EMR, so whenever you EMR, it's all of them, right? So radio, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays. They're all the same disturbance in the field. It's just how fast it's jiggling versus the size of the wavelength. Now, they've had to show you the red is the electric field and the blue is the magnetic field. Now, this field is everywhere and it doesn't require a medium. If I take a charge and I jiggle it, I want you to imagine the electric field rippling in response to my disturbance of the electric field. The analogy is you go to the surface of a pond and you give it a bit of a jiggle and you see those ripples travel out. On a 2D plane, you can see those spherical wavefronts travelling away from the ripple. Now, the electric field is three-dimensional. So instead of a 2D plane, think of 3D volume. And if I take my electric charge and I jiggle it, think of these ripples travelling out as a sphere. And they're travelling out at the speed of light. Now, there was a very famous bloke called James Clerk Maxwell back in the early 1900s. He looked at how electric fields changed in space, and it involved a certain physical constant called the permeativity of free space, which they'd measured. And he looked at how that interacted with a magnetic field. And then he looked at how the magnetic field changed in space, and it had another equation that had a constant called the permeability of free space. And these both had been measured in experiments, ones with magnets and ones with electric charges, right? He realised that changing one changed the other. And he did the vector cross product of the two vectors and outspat an orthogonal vector, and it had the value of 2.9975843 blah 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 meters per second. So he actually was able to show that light is an electromagnetic wave, and it travels orthogonal or at right angles to the two. So you've got your electric going up and your magnetic going in and out, and so the orthogonal vector that now travels off at the speed of light. So he was able to pretty much prove that light travels at that speed, that it is a transverse wave, it doesn't require a medium. So that obviously that makes sense to you, I hope, that we can get light from the sun. There's a vacuum between us and the sun, 150 million kilometres between us. These ripples of light are travelling, and they're travelling really, really fast. It takes 8 minutes for these ripples to reach us, and then it comes down and gives us life and all the good stuff. So that was cool, and he was very famous for it.
When did he live?
Late 1800s to mid 1900s, James Clerk Maxwell. I just lost my train of thought because I'm thinking, what is Jake and Harry looking at on the laptop? What are we looking at? Right. Thanks. Now I have to think, what the hell am I talking about now? So, transverse wave, that's light. Just back onto our booklets, please. Let's just scribble down our direction, V. Oops, try again. Now, even though it's been measured to like 9 or 10 significant figures, to 3 sig fig, it's 3.00 times 10 to the 8 meters per second. Okay? And so that is the speed of all electromagnetic radiation
In a vacuum.
in a vacuum?
Units slower than
It is. Is that how you spell vacuum? No.
Just write it.
Close.
Just write VA.
To be continued. That's right. This I've just remembered before Harry and Jake rudely interrupted me. The cool thing about this animated GIF is that Maxwell was able to show, where's me? There we go. That it has to travel at that speed. Using his famous equations that I was talking about, how the electric field changed the magnetic field, and the two equations that explain them. If it went too fast, then the electric field would get too big and the magnetic field couldn't keep up, and so it would basically fizzle. And if it went too slow, then the opposite would occur. Then the magnetic field wouldn't be going as fast enough and it would fizzle. But at just the right speed, they self-propagate. And that's why it can travel in a vacuum. That in order to make a red ripple, you need a changing blue ripple. And in order to make a blue ripple, you need a changing red ripple. So you get this self-propagating. Is that right? Oh, I can't do this. You've got to have a 3D. So that one's doing that. Right? So do that with your left hand. Right? And then do the other plane with you, and then travel forwards at the speed of light. Right? It has to go at that speed for this self-propagation to occur. It can't go faster and it can't go slower in a vacuum. Now the next thing, gents, so it's 2.997548 something. The next convenient thing for you guys and for the year 12s is it actually does slow down in air because it's interacting with atoms. It's being captured and re-emitted and it's interacting and bouncing off. It does slow down, but it only slows down by about 0.1%. So if you took this number, or the real number, 2.99758, blah, 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 and you reduced it by 0.1%, in your calculator it spits out a different value, but when you round that number to 3 sig fig, it's still 3.00. So that's convenient, that the speed of light in air is the same as the speed of light in a vacuum to 3 significant figures. It might affect the 4th or the 5th, but as far as we care, 3.00. Yes?
Can I explain why light doesn't travel through objects slows down to a point where it's getting back to a harder
Well, no, because you can get really thick blocks of glass versus you could get a glass block the size of a brick. It has to do with how the atoms are arranged, whether it's homogeneous or heterogeneous, whether it can be transferred or whether it can be reflected. So to be short, I'm not quite sure why things are opaque versus translucent versus transparent. Depends on the atoms and whether they will grab certain wavelengths or allow them all to pass through or none at all. Probably the atoms and the bonds between the atoms are going to affect what, if any, light is captured or reflected or transmitted. Over the page, gentlemen. This paragraph should really have been on the other page. Both longitudinal transverse waves can be modelled by a sine wave. So if we go back to, I'm making you jump all over the place. If we were to plot the position versus time of this red dot, left, right, on a y-axis, you are going to get a sine wave. Okay? And same with a transverse wave. If we were to take one of these dots and go up, down, well, hey, that is pretty much a sine wave because we're seeing the displacement in the y-axis. So again, over time, we would see a sine wave. And so we can model them with some equations. This is not in the syllabus, but the equations can be written as such. What? Don't worry. Okay, don't worry about that. Just Yeah. Forget I said anything. Cool. I'm glad I had the right symbols and everything. All right. So, guys, think back to the longitudinal sound wave GIF that had the moving metal bar pushing the particles around, and we've just taken a snapshot of this. Obviously, you should be able to see areas where they are close together. I would like you to write C above each of these bands where the particles are close together. I would like you to call them compression. Okay, so that is an area of high pressure. And then directly in between each area of compression, I'd like you to write capital R, and that should be areas where our particles are spread out. And we are going to call those areas of rarefaction. And that is areas of low pressure. Okay. Now, our speaker is obviously jiggling backwards and forwards with a certain frequency and providing a few things that the speed of sound is constant. They seem to be nice and regularly spaced. So this is called simple harmonic motion. And that's where your disturbance is just a constant frequency. Okay? It's not speeding up or slowing down. It's just boom, 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 boom. Nice and regular frequency. And so we take a snapshot. All of these regions should be nice and equally spaced. Okay? Again, it's a snapshot in time. If we took a snapshot a fraction of a second later, we would see these particles would be moving. These particles in high pressure are going to try and fall back into the areas of low pressure. Okay? Because remember, this is currently under 1 atmosphere. We are under an immense amount of atmospheric pressure pushing down on us and around us and into us at all angles. And so if we can take a section of air and suddenly expand it out, it's not going to last long because the pressure is going to push everything back towards each other. Okay? That's just what air and wind and gases, that's what they want to do. They will always go from areas of high to low. We've created a disturbance. Now, this will appear in a future lesson, but let's just take the distance between each successive areas of high pressure. And if I've drawn this diagram correctly, they should all be equidistant, or at least they should be. And we're going to call this the wavelength. More on the wavelength in future lessons. Okay? So again, hopefully I've drawn them correctly. And the wavelength has the symbol lambda. Okay? Greek symbol lambda. I have pinched/borrowed just a couple of further diagrams. So again, the picture above kind of looks like this, as we can see about 6 or 7 regions of compression. This diagram is showing 3, but if we start back here at the start, all the particles are nice and evenly spaced. They're in their equilibrium positions. Okay? So let's just add this term, equilibrium position. And that is where the particles would like to be. That is where the particles would like to be if there is no net force acting on them. So that would be a swing would be stationary at its lowest point. A guitar string would be nice and stationary. The surface of a pond would be nice and level. All of the air molecules are nice and evenly spaced. Then if you apply a pressure wave to any of those or a disturbance, those particles are going to be disturbed from their equilibrium positions, either going up or going down. Okay? Either going left or going right. And they want to go back to their equilibrium positions. Let's continue over the page. Yes. So, guys, this equation is not in the syllabus. You may have seen it in spec maths or math methods. You might have encountered it in extension maths in year 10. However, A is simply the amplitude. Omega is known as the angular frequency, which is sort of 2 pi f. And then this little buddy here is known as the phase shift, which generally we ignore because we set the phase shift to 0 because we really just plot it from the start. Sine of 0 is 0, and then you make your sine curve from there. How high your sine curve goes depends on the amplitude. How many sine curves you have in a given period of time depends on your angular frequency. But you can play around with all of these. You're simply going to be making a sine curve. It's either going to be stretched out, shifted left or right, and stretched upwards or downwards, playing around with the amplitude and the frequency. Yes, Marcus?
Surely it wouldn't be a phase shift though, because phase shift would be inside the sine function.
Yeah.
Would that be like rest pressure or something?
What
Rest
should my
pressure?
bracket be?
Well, I'm just thinking,
Yeah.
if it was phase shift, it'd be inside the bracket.
Yeah.
Right.
Yeah, okay, I stuffed up. The bracket should be outside. That would be an amplitude shift. That would be translating it vertically.
Yeah, like rest amplitude or rest pressure.
Yeah.
Just do another.
Not in the course, don't worry about it. What is in the course, however, gentlemen? So, here's where I need you to understand. We are now looking, this is a amplitude displacement graph because it's telling me that this is the distance from one crest to another. So this could be making a wave in water, standing back and taking a snapshot. And you can see, in the picture, you can see two waves. And in that picture, you can measure how far apart the waves are and how high above the equilibrium position the waves are. So again, if you stood to the side of the water and took a picture, this is what we would see. Okay? So could you please add a few bits here? B is the equilibrium point or equilibrium position. Equilibrium. Okay. In which case we then have what we're going to call crests and troughs. A crest is the highest displacement from the amplitude, how high the wave gets above its equilibrium point, and then the trough is going to be how low it gets below its equilibrium point. Okay? As we said, amplitude is a measure of displacement from one to the equilibrium. Now, if we're not losing any energy, if this was no energy being lost, then obviously all of those amplitudes are going to be the same. But if you followed a wave, if you could sort of follow alongside a wave in a pond, you would see it slowly losing energy to heat. But anyway, we're not going to worry about losses of energy. The last one, gentlemen, is the wavelength. And that is our distance between successive crests. Oh, the laptop is struggling. The distance between successive crests or successive troughs. Or one sine wave. So there's a couple of ways we could do that. We could do that. Okay, so there are 3 methods, Mitchell. 3 methods. And depending, you might be given a picture, you might be given a graph, and you might not be able to see a crest to crest, or either way, if you did one sine wave, so there's a nice sine wave, or crest to crest, or, sorry, crest to crest, or trough to trough. Hang on, I've stuffed up, haven't I? I'm going to take, I have stuffed up. Where is my trough to trough? I'm going to take him and chuck him down. Oh, there is no trough. Ah, okay. See? Perfect example. We cannot measure trough to trough because this graph does not show 2 troughs. It shows 2 peaks, so we can do that. Okay? All right. Down here, please. Providing a constant frequency then our wave should have a constant wavelength. So if I take this measure of peak to peak and call it lambda, I should be able to slide this down anywhere along this graph, and I'm always going to be on the graph. Okay, so I could place it down here, and hopefully the image that I've stolen is a nice anywhere. And so if you just go Control C and Control V, or you get your rulers out, you should be able to notice that peak to peak, trough to trough, or one sine should always give the same distance or same length.
Would be any 2 points, right? So, like you can put the thing halfway up.
Yeah, so what we'll get to in tomorrow's lesson is if I just went anywhere here, so I just placed it there and said, let's pick these 2 points, point A and point B. We say that point A and B are in phase. They're in the same position and they're doing the same motion. So they're both this high above their equilibrium point, and they're both traveling upwards. We'll learn more about it. If the wave's traveling left, then they're both traveling upwards at the same speed and at the same point. That will come in tomorrow's lesson. Have we got 5 minutes left?
Yes.
All right, let's just chill for a bit, because I'm going to load up a couple of fun videos.